Hello, today we are going to look at using quadratic functions to model the real world. So, is there a physical process that goes on that behaves quite similarly to the way a quadratic function behaves? And if there is, then we can model, we can describe the world using that quadratic equation. And this is something that we would do in science or in business or in lots of things where we want to understand the world well. We'll find a function that matches the pattern we see in nature, and often we will look for simple things like quadratic functions because they're nice to work with, relatively speaking. And in the exam style questions of these, we will get stories and we will have to interpret the language of the questions to figure out mathematically what they're talking about. So let's have a look at our first example. We have a device that measures the apparent height of the sun above the horizon. If we don't look at the sun, but if we try to look with a device looking at the sun to make it safe, how high does it look like it is above the horizon? Using the particular device, we would measure the height it appears to be above the horizon line in centimeters throughout our day. So our time is in hours going across the x-axis, and its Greenwich Mean Time is what I have plotted across the x-axis in hours, and then we have the height that our device measures the apparent height of the sun with in centimeters. And we need to be careful whenever we get these kind of graph questions, what units are we working in? So in this case, the height that we measure the sun above the horizon, the apparent height of the sun above the horizon, each little box is 1 unit, 1 centimeter, because we're going up in fives and there are 5 little boxes going up. So we're counting up in ones with our little boxes here, but we're counting up in ones with our big boxes going across the x-axis. So often we need to be quite careful and figure out what is our axis telling us. How are we counting in the y-axis and in the x-axis? So if we think about the path of the sun as it goes through a day, it starts off at daybreak at the horizon, and then it rises up to its highest point, and then it will drop down. It will be low in the sky in the evening. So that's what we're looking at here, that the sun throughout the day would be at different heights. So it's not that it's moving east to west in this picture. This is the height of the sun as the time goes by, or the apparent height of the sun, I should say. The graph is given by our function for s of t, which is a fairly messy looking quadratic, but we'd be able to put it into our calculator. So let's get into our questions. When does the sun appear 15 centimeters high? So when does it appear to be 15 centimeters above the horizon? So we're looking at height. So we go to 15 centimeters on our height. We go across that line and we hit our grid here. Well, what's the coordinates of that point going to be? That's going to be up the stairs 15, and if we drop down from that point, we would get 8. So that coordinates of that point would be at 8:15. So that's going to happen at 8, and I can see from my graph here that's probably going to be 8 a.m. or 8:00. And continuing on to find the other coordinate, because I can see it's going to happen again. I come here and I'm about halfway through that box, so I drop down in between the two lines there, and that is halfway between, pretty accurately, that's halfway between 15 and 18. So that's going to be 5:30 p.m. or 17:30. It's also worth considering, how would we do this algebraically? Well, we know that s of t, the height of the sun, the apparent height of the sun, is given by this equation. We want to know when the height is 15 centimeters. So we could simply set this quadratic equal to 15, get everything over to the left-hand side, and solve it using the minus b formula, or factorizing if we could. Again, this is the quadratic. We'd set it equal to 15. And we would get everything over to the left-hand side and solve using the minus b formula or factorizing to find our values of t, to find the values of 15 and about 17.5. Now, when is local noon? So what does noon mean, or local noon mean? Well, that means when is the sun highest in the sky? So I would look to where the sun is highest in the sky, and that looks like it is about there. So that is approximately the highest point we've got. So if we go down, following that carefully, we are at 12 and we are on the fourth mark over there. So that would be 12.8 hours. And we wanted to give that in hours and minutes. 0.8 of an hour would be 0.8 of 60, which would be 48. So that would be 12:48. Again, 0.8 of an hour is 0.8 times 60 minutes is 48. So you could say that is 12:48 p.m. There's another thing to note about this, however, because we know that a quadratic curve is symmetric, and we can see that the roots of this quadratic are at about 5.5 and 20. So we know that because the curve is symmetrical, that means that the highest point is going to be halfway in between our two roots. So we could also get the average of, get halfway between 5.5 and 20. And we could see if we got the same result. But if we're asked to read it from the graph, this is the form of the answer that we would give. I'll write it in the other way here. We actually happen to get 12.75 as opposed to 12.8. However, in an exam, if we are asked to do this graphically, that is what we do. If we're asked to use the graph, we are drawing in our dashed lines to show we used the graph, and that level of inaccuracy is perfectly acceptable. It is, however, important to remember that we have this symmetric aspect to our quadratics, that they are effectively mirrored in this dashed line here. Next question, how high does the sun appear at local noon? So at local noon, we are at this point, so we would go across as neatly as we could. And we would be careful again about what units we are counting in on our y-axis when we've gone across. So I've gone just slightly above one block beyond 25, and I know each little block here is 1. So I'm very slightly above 26 centimeters, but 26 centimeters would probably be acceptable here. So 26 centimeters. Pardon the maneuvering. So we have the height at noon. What does it mean when s of t is less than 0? So s of t less than 0, well, less than 0 means negative. So what does it mean when our function here, s of t, is negative? Well, s of t is the height, or the apparent height, of the sun above the horizon. If we're down here, if we're down in these tails here, that means that the sun is below the horizon. That means it's nighttime. Now, when is sunrise and sunset in AM, PM? So all we are looking for, and I've actually made reference to it here already, where the sun comes above the horizon is sunrise, when the sun drops below the horizon, it's sunset. So all we are going to read off is our 5.5 and our 20 and convert them to AM and PM. And to reinforce the language we'd be looking at, we're looking at the roots of the equation, where we are crossing the x-axis, the height axis in this case. So we would have our quadratic equal to 0 for our height being equal to 0. Now, a ball is thrown vertically up. Its height is given by h of t. So we're dealing with changes in time, t for time, just like we were before here. This time our time is in seconds and our height is in meters. What is the height of the ball thrown from? So what height is the ball thrown from? Well, it's thrown at time is 0. That's when it gets thrown, and that is happening at a height of 2 meters. We can also get that from using the quadratic itself, because this is the height through time. So if we set time equal to 0, that's when the thing gets thrown, that's going to be subbing 0 in for t, and then we're just left with 2 for our 2 meters. What is the maximum height and when is it reached? So the maximum height, if this is measuring the height, then we look for how high up we go. So we've traced across here for our maximum height, and then we have to be very careful of what units are we counting in our height axis. Well, we can see we're going up in 2s, and there are 5 little marks each time. That means 5, how many, if we are going up in 2s and we do it in fifths of a box, that means we're going up 2/5 or 0.4 each little box. So each one of these little boxes is 0.4, and we're going up through 2 of them and then halfway up another one. So that means that we're going up by 0.2, 0.4, 0.8, and then 1. We've gone up to 11. We've gone halfway through one of these boxes, so it makes sense. Say here would be 9. We're halfway up. So our maximum height then is going to be 11 meters. And when is that height reached? Well, then we have to be careful here. We're counting in 1s in big boxes here, and we're still going across in fifths. So that would be 0.8, and we're halfway up to 1. So that's going to be 0.9 of a second. So 0.9, and we have our units of a second. When is the ball 8 meters from the ground? So we mark across at our height of 8. And we find the coordinates of those points. So we drop down here, and that would be at 2 boxes over. So at 0.4, 0.4 seconds. And here we've gone across, and we would be at 1.5. We're halfway through our box from 1 to 2. So that would be 1.5 seconds. And algebraically, it's worth considering that we are looking for when the height is 8 meters. So we would take the height function and we would set it equal to 8. When is the height 8? And you're looking for your values for t. So when we rearrange that, because we recognize we have a quadratic, we're solving this quadratic to find the values of t. And approximately from the graph, they were 0.4 and 1.5. And if we're asked from the graph again, our workings are to show our dashed lines on the graph to demonstrate we are reading from the graph, and we understand how to do that, that we're finding the coordinates of these points effectively. Now, when does the ball land? Well, we're measuring the height above the ground, and it hits a height of 0 after 2 seconds. So when does the ball land? It lands when it hits the ground after 2 seconds. And that is how we read our quadratic graphs to get information from them. That's how we tell ourselves the story of these real world problems if we get them in our exams. And that is what we need for now.